So we ended last day saying there was two definitions for work. Work was force times distance. Force had to be constant. Distance had to be in the same direction as the force. Or it was the area under a force versus distance graph. Example 8. Darce, what does example 8 want me to find?
Work.
Done doing what? Read me the whole thing.
How much work is done in moving this unknown object?
Moving this mystery object from here to here. Well, I can't go force times distance. The question didn't give me, well, they sort of gave me a distance. Wait. They gave me a graph. Darcy, what is on the y-axis? What is on the x-axis? The work is going to be the area. It's going to be the area underneath this shape. Don't color it in, but it's going to be that area. It's a trapezoid again, but I think I went on a rant last day. I said we don't need the equation for a trapezoid because any trapezoid can be broken into which two shapes? Triangle and rectangle. That part you'll have to figure out how to do yourself, but hopefully you can see area 1, there's the triangle. Area 2, there's the rectangle. I can't help you do the breaking it into shapes part. That, Taylor, you've done enough since your kindergarten breaking shapes up. Hopefully you can spot it. If you don't know the formula for the area of a triangle, you can add that to your formula sheet, but it is base times height divided by 2. Darcy, my friend, how long is the base of this triangle? Look at the graph and look at the numbers and figure it out. Yep. What's the height of this triangle? Don't say 30. Yep. Divided by 2. In your head, what's 10 times 10 divided by 2? Thank you. And the units for work is joules. Area 2, it's a rectangle. The area for a rectangle is length times width. Darcy, my friend, what's the length of this rectangle? What's the width? 20. It doesn't matter whether you go width times length or length times width. It's, base times height, whatever you want to call it. Anyways, it's 10 times 20 in your head. So, what's the total amount of work that it took in your head? 250 joules. Is that okay? You good, Thomas?
Yeah.
You have the notes in front of you?
Yeah.
You're not trying to build a little tower hiding your phone behind you or anything like that? Okay, because it looked a little suspicious. Let's try and put everything together here. It says this: a box is being pushed along a floor that has a coefficient of friction, mu, of 0.25. The person pushing applies a force of 525 newtons over a distance of 22 meters. Connor L., what's A asking me to find? Well, work equals force times distance. I'm kind of imagining, I guess we're pushing a box along a floor, but you can feel friction resisting you in the other direction. You've probably all experienced that at least once trying to slide something heavy across the floor. Okay. What's the force done by the pushing? You know what? I think it's actually, in this question, the applied force, because it says pushing applies. Is that okay? What's the applied force?
500.
Do a quick check. Is the applied force in the same direction as the distance?
Yes.
So what's the distance?
500.
What's the distance?
Oh, 26, sorry.
There you go, Captain Obvious. Yep. Which is what? I can do this in my head. 525 times 20 is going to be 1,500. Then plus 1050. 11, good gosh. 11,550?
Yes.
Units, Connor? Work. If you're not sure, look at the previous example.
Oh, joule.
Yeah. Okay. Newton meters, but we've called that a joule. That's how much, let's pretend it is Connor. That's how much work Connor did in pushing, but not all of that energy went into moving this box. Some of it went into overcoming friction. What does B want me to find, Connor, my friend? I'm going to argue, I think, work equals force times distance. If it's the work done by friction, I think it's the force of friction times distance. Fair, reasonable assumption? And you're going to find for the work equals force times distance equation, Simi, we tweak it to fit our specific situation. We already did that when we were lifting. We said it was mgh. It became force times distance, mgh. Here, friction. I think this is a job for a free body diagram, and my thinking that way is the fact that there's a mu. I'm going to try and build as much review into the actual questions as I can over the next few lessons. So let's do a little bit of forces review. We're going to represent the box with a dot. Connor, what are the forces acting on this box? Get the obvious one. Is it sinking to the ground like quicksand? Is it flying into you like Superman? So the ground must be pushing back up. We gave that force that any surface exerts pushing back up a special name. Yes, Fn. Finally, all of you have an Fn clue. Excellent. There you go. Thomas liked that one? Okay. What else? And let's pretend you're pushing it to the right, and that's going to be F applied equals 525. What else? Which way? Yeah. Okay. I've got the setup now. And I'm pretty sure friction is smaller. I'm pretty sure this thing is accelerating. But if not, we'd figure it out when we did some calculations. We could tweak it. Okay. Now, let's keep going here. Back to our work. Force of friction times distance. Well, friction is what times what? Oh, mu times the normal force. And then the distance is still tacked on because we're doing work. I got a problem. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? Ah, so mu mg times distance. Okay. The work done by friction is going to be, hey, Connor, what's mu? I don't know what's mu with you. What's mu? 0.25. M was 124. G, yeah, and not negative because we're in scalarville here. Work is a scalar. D. Oh, pause. We forgot to do our quick check. Is the force constant? I think so. Is the force in the same direction as the distance? Which way is this box moving? To the right. Which way is friction pointing? To the? So let me ask you again. Is this force in the same direction as the distance? It's in the opposite direction. Same plane, same level, opposite direction. How could I show opposite direction? This negative is actually not a direction. It's a scalar. Crunch the numbers and I'll tell you what this means. What do you get? 6,873? Isn't that right? Oh, hang on. No. My bad. I missed a time sign there. Let's try that again. 6,684 if you had rounded off properly. But we'll write the whole thing. 6683.6 joules. What does this negative here mean? It doesn't mean backwards. Actually, it means you lost that much energy to friction. Where? Have you ever noticed if you rub your hands together, it gets hotter? You lost that much energy heating up the floor. So you put in 11,550 joules of work energy, but 6,683.6 joules of that went into heating up the floor. Only the remainder went into making this box speed up. What is the net work done on the box? What was left over? Well, the net work is going to be the work done by the applied force, take away the work lost to friction. Except it's not going to be a minus here. What I really mean is that negative is that negative there. You're losing energy. So part B, you could have called it a positive number and just called it a loss. You could have said 6,683.6 joules lost to friction, because lost implies a negative. Or you could just call it a negative. If you called it a loss, you would say the total work is put in, take away lost. Here, it's going to be, so I just don't want you to think there's a minus here showing up out of nowhere. What was it? 11,550 minus 6,683.6. And I get 4866.4 joules of work. Your homework but I can't just pause. I want to get 2 lessons done today. We are going to get 2 lessons done today, and that's going to give us a full review period. So you are going to have homework for Thursday. You have almost a week to work on it. Pause. I went on a big rant last day saying work is not tiredness. You know what is tiredness? Power. If you're getting tired, it's because your body is generating more power, not because you're doing more work. It's the different, well, ready? The definition of power is this. Power is the rate at which work is being done on an object. It's how fast you're working. It's not how much you're doing, it's how fast you're doing what you're doing. Thankfully, the symbol for power, capital P. By the way, capital P power, lowercase p momentum. Sorry, don't have enough letters in our alphabet. Anytime we have the rate at which something is done, we really mean you're dividing by time. Power is work over time. I'd like you to look at that. So as an example, what's more tiring, walking up a set of stairs or sprinting up a set of stairs? Sprinting. Why? In both situations, you're doing the same work. You're doing the same MGH. Less time, dividing by a smaller time, bigger power. The stairs in the back corner field there are so shallow because that's what allows senior citizens to do that work. We spread it out over a longer time, and they can handle that okay. Where if the stairs were steeper, or if it was a ladder, you guys could probably scramble up the ladder in less time doing the same amount of work, but most people couldn't generate that much power. They would find it too fatiguing. So if you're getting tired, because you're generating lots of power, it's the difference between walking around the block and running around the block. You're doing the same amount of work. It's the difference between walking up a hill and running up a hill. You're doing the same amount of work, less time, more power, more fatigue. What are the units for power? Well, what are the units for work, Connor? What are the units for time? It's joules per second. But this unit is so important, we give it a special name. Power is measured in what? Watts. Symbol capital W. So capital W after a number is the unit watts. Capital W in an equation is work. Sorry. Again, we need more letters in our alphabet. Power is also a scalar. Suppose an electric motor is used with a pulley and a rope to lift, underline the word lift, that tells me a great deal, a 650 Newton load from the road up to a height of 12 meters. The job is done in a time of 11 seconds. What's the power output of this motor? Thomas, what does this question want me to find?
Power output.
Yep. Power is work over time. By the way, this is also on your green sheet. I think it's right next to the work equation, I think. Work is what times what? So power is actually force times distance over time. When you lift, which force are we doing work against? Gravity. And the equation for gravity was? mg. In fact, we said when you lift, you could modify the work equation to become mgh. We called the vertical distance a height over time. Thomas, what's the mass that we're lifting?
650.
Newtons. Ah, wait a minute. Right there, that's not a mass, that's a weight. They gave me mg, so I don't need to multiply that by 9.8. Apparently, they've already done that for me. So I can just say 650, that's mg, times the height. What's the height, Thomas?
12 meters.
12 meters, around 4 stories-ish, a little less. Divided by, what's the time?
11 seconds.
Okay. How many watts of power did this motor give us? What's the power output of the motor? I get 709.1, 709 watts. Now, power is measured in watts in the metric, in the SI standard system. In the imperial system, power is measured in horsepower. What a stupid unit. Any of you know how much power a horse is capable of generating? We should have phased this unit out a long time ago. It was useful 250 years ago when everybody and their dog was familiar with horses. But most of us are not familiar with horses now. But it stuck around. I'll tell you the story behind it a bit later. But for what it's worth, 1 horsepower is almost bang on 750 watts. So this 709 watt motor has a horsepower of what? I need to do a unit conversion. We did that at the very beginning of the year. Who remembers, whenever I did a unit conversion, what was the first thing I always did, just as a start? Haley, what? I wrote down what they gave me, 709 watts. Because now I would say, oh, I want to get rid of the W, so I'm going to multiply. If I want to get rid of the W, where do I want the W in my next conversion fraction, on the top or on the bottom? And the bottom, and I guess horsepower is going to go on the top. Do I have a conversion factor? Yeah, I just underlined it. Apparently, 1 horsepower is 750 watts. And here's the key. It tells me what to do with that 750. Because the 750 is on the bottom, divide it, not times it. Right? Takes the guesswork out. So it's going to be this number, which is still on my calculator, divided by 750. It's just shy of 1 horsepower. 0.95 horsepower. If I ask you to convert something to horsepower, I assure you I will give you the conversion factor. You do not need to memorize that 1 horsepower is 750 watts. We got better things to memorize than a stupid imperial unit. Next example, a 60-kilogram girl runs up a flight of stairs, 3.32 meters high. 3.32 meters, about 1 story-ish, in 2.6 seconds. So you know what? Imagine the stairs in the back corner of my over there by my classroom, running up that in about 2.6 seconds, which is not crazy quick, but quick-ish. What's her power output? Well, power is work over time. And work is force times distance over time. When you climb stairs, which force are you doing work against? In fact, you know what? I think this is the same mathematically as lifting an object. It's going to be mgh over time. 60 times 9.8 times 3.32 divided by 2.6. How many watts of power is this girl generating? 751?
Yeah.
Basically? And if 1 horsepower equals 750 watts, what's her power output? Almost exactly 1 horsepower. So if you want to know what 1 horsepower is, you can run that set of stairs over there in about 2.5 seconds. That's about 1 horsepower of power. The horsepower comes to us from an engineer named James Watt, and he's a little, to me, overrated, because he has this unit watts named after him, and all of you have heard of the unit watts because we live in an electric society. By the way, next year I'll show you that we can take that work over time and we can redefine it in terms of current and voltage, and we can get electric power in watts. It comes out of this, though, starts with work over time. He was an engineer around 1750-ish or so. He didn't invent the steam engine, he improved the steam engine. What he really was good at was selling. You see, he was going around to farms and he was trying to convince farmers to buy a steam engine to do work on the farm. And here was his brilliance. He invented the horsepower as a unit. So if you're a farmer, Darcy, and he says to you, this engine has 4 horsepower, you immediately think, oh, this will replace how many horses? 4. It doesn't. It has. It's nothing close to what a horse can do. It's a made-up unit, but it was a brilliant sales pitch, because instantly now you're thinking, okay, 4 horses, they eat this much food, that costs this much a year to maintain. How much? Yeah, I can. You know what? I'll come out ahead if I buy your steam engine, which is nonsense. He made up the unit, but it was a brilliant sales pitch. In fact, so good we still use it, even in a society where horses are not part of our society anymore. So he was a little overrated. I wish they hadn't named the Watt after James Watt. They should have named it after someone else, I think. But we're stuck with it. Example 2. Christina, what are they asking me to find in example 2? Time. You know what? Let's fall back on our DFIC approach. We've kind of abandoned it as we've gotten good, but let's fall back on our write down what they gave me, T equals question mark, and let's walk through and see what else they gave me. Christina, what's that 10.0? Power. I don't like the units. So I'm going to write P equals 10 horsepower, but now I want horsepower to cancel. I guess in my next fraction, Christina, it's going to go on the bottom, and watts is going to go on the top, and I guess it's going to be 750 over 1. I guess, Christina, it's going to be 750 times 10. In your head, please, how many watts? You didn't need a calculator for that, right? Whew. What's that 500? Mass, right? What's that 30? Oh, you know what? It is a distance, but if I underline the word lift, rather than calling it D, what letter have we typically used instead? Let's go H equals 30. And I think I have a pretty good idea of where I'm going. I'm going to start with my power equation. I'm going to say power equals work over time. But what am I trying to find, Christina? What I want to get by itself? What letter? Where is the T right now in the bottom? Ugh. We can't do math with stuff in the bottom of fractions. Wait. Dividing by T on the right is the same as what by T on the left? So are you telling me that really that's the same equation? Yes, it is. Now, how would I get the T by itself, Christina? Yeah. So yet another equation, yet again, please don't memorize it. We can derive whatever we need to derive. Apparently, time in this situation is the work divided by the power, where work is force. Oh, you know what? We're lifting, yes? MGH, isn't it? Divided by power. And now I think we can calculate how much time this will take. Mass, 500. G, 9.8. H, 30. Divided by power, 7,500, not 10. What do you get? Units? Here's what that means. It's impossible for this motor to get this job done any quicker. If you need it lifted faster, you need a new motor, a different motor. Now, in this situation, big deal. You know what? Instead of lifting a safe up to a window, look at the big cargo cranes that unload the container ships. I guarantee they know how many watts of power those cranes are able to exert, how long it takes in them to lift a container up, then they move sideways and drop it down. They've run the numbers, and that's how they know how long it takes them to unload a container ship. And they can't go any faster if they're maxing out the power. You can't. I want to go faster. You'll have to replace the crane. Sorry. You're stuck with your power. That's how much work you can do per second. That's how much joules of energy you can exert per second. Power is also measured in kilowatts. If you get your hydro bill, once you're moved out on your own, you'll find your hydro bill is kilowatt hours. That's how much energy you use, because a watt's pretty small. It's also measured in megawatts. They typically will talk about hydroelectric dams producing megawatts of power, because a watt's pretty small. So 1 kilowatt is 1,000 watts, 1 megawatt is 1,000,000 watts. Example 6. Power of a light bulb is the amount of electrical energy it consumes in 1 second. So a 40-watt bulb uses 40 joules in 1 second. What's the power rating of a bulb that consumes 4,200 joules of energy in 70 seconds? Brian, what's this question want me to find? Well, power is work over time. Brian, what are the units for work? How many joules are we using here? Yeah, by the way, if you're wondering, what work is that? It's the work done moving the electrons through the circuit. How much time? So if you have a light bulb that uses 4,200 joules of energy in 70 seconds, how many watts? It's a 60-watt bulb. In real life, you'd reverse it. You'd know the wattage of the bulb, and you'd like to know how much energy I'm using if I leave it on for 4 hours, if I leave it on for 9 hours. What's it going to cost me? We'll tackle that in Physics 12. We'll spend a lot of time looking at electrical power. Turn the page. There is a special version of this question if we are moving at a constant speed. There is a special version of power if we're moving at a constant speed. Sydney, what's the equation for power? Power equals what over what? W over T? That's right, yes. That's on your sheet. I'm going to show you a hidden equation, and I deliberately did not put this on your sheet. I'll show you how to derive it. Work equals what times what? That's for lifting. The generic equation for work on your formula sheet that Lyndon has right there that you can go look at on the green sheet. W equals what? So ready? Let's all write F times D over T. With me so far? I would like all of you now to circle those two letters like that. Sydney, D, the top letter, D. What are the units for D for distance? What do I measure distance in? Meters. T, what do I measure time in? You know what? This is meters per second. What do I measure in meters per second? I got to be fussy. We're in Scalarville. Speed. Okay, velocity, speed. Another equation, another way to calculate power is force times constant speed. When do I use that? If they say how much power and they don't give me a time, but they give me a speed. You want a good example? Bike riding. Let's imagine you're riding your bike and you're going at a constant speed, so you're exactly canceling out air friction, air resistance. How much power would you be generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at exactly 12 meters per second? So I would start out by saying, yahut, they want me to find power. which is work over time. Then I would say, Sydney, work is force times distance over time. I would say, did they give me a force? Did they give me a force? Yeah. I would say, did they give me a distance? Did they give me a distance in this question? No. Then I would say, what else did they give me? A speed, and hopefully that's enough for you to realize, hey, meters per second. Is that okay, Connor? You're not foolish looking at your phone or anything like that, are you? You're good? Okay. Connor, my friend, what's the force that we're exerting in this question? And how fast are we going? That's how much power you're generating. 32 times 12. I can do that in my head. It's going to be 320 plus 64. 384? Yes? 384 watt? Power. Tiredness. If you're generating more power, you're getting tired faster. If you're generating less power, you're not getting tired as fast. It's the difference between slowly doing work and quickly doing work. Efficiency is another concept in physics. We talk about how efficient objects are. It's sort of how much bang you get for your buck. It's how much of the energy or the power that we're supplying goes into useful stuff, and how much of it is wasted, typically as heat and sound and other dissipative forces. Internal combustion engines, car engines, are terribly inefficient. A lot of the energy is just wasted as heat. Electric engines, the reason electric cars, hybrids, get better mileage is electric engines are more efficient. They don't give off as much heat. There is a symbol for efficiency. First of all, you can just write EFF for efficiency. In fact, that's what I did for years. I only found out that there's actually a physics symbol for efficiency a few years ago. Or the symbol for efficiency is the Greek letter eta. ETA. What is the Greek letter eta, you ask? What is the Greek letter eta, you ask? I'm so glad you asked. The Greek letter eta looks like a lowercase n, but written in cursive in handwriting with a droopy tail. Ready? Looks like this. That's an eta. It's a lowercase n with a little droopy tail. You can use that if you want to, because I know some of you are enough of a nerd and like to abbreviate. You're like, hey, shortcut. But if you just write the word efficiency or write EFF, I'm totally fine with that. In fact, you'll notice in most of my answer keys that are handwritten for Physics 12, because I made those answer keys before I knew about this symbol, I actually wrote EFF all the time. But since I have a handy-dandy schmandy symbol, I'll use it. What's the equation? How do we calculate efficiency? Well, it's power out divided by power in. Or work out divided by work in. Or, we haven't talked about this yet, but I'll stick it in there, energy out divided by energy in. That'll give you a decimal, and then you multiply by 100 to change it into a percent. The same way as when you figure out your test percentage, you get a decimal on your calculator, and then you times it by 100 to make it a percent. No one memorizes that. Well, I mean, you can. Here's what I know. It's impossible to be more than 100% efficient. Efficiency will always, in our universe, be less than 100%. If you have invented something that's more than 100% efficient, what you've just done is you've solved the energy crisis. You've invented a perpetual motion machine, and in about 4 years, you'll be able to buy Bill Gates. About 10 years, you'll be able to buy an island, a country. they'll name a unit after you. You'll get a Nobel Prize. You will have, if we had unlimited energy, if we had free energy, unlimited, honestly, even with our current level of technology, if you gave me a free energy source, we could pretty much engineer our way out of anything. Oh, need more food? We can have lights going on all night. We can have the plants getting sunlight 24/7. We can grow more food. Done. If you give me free energy to power the lights. Oh, and to build those lights, if you give me free energy to power the factory, that's a win too. But it's impossible. Our universe will not let us have anything that's more than 100% efficient. Can't be done. So, you ready? Here's Mr. Dewick's better version of this equation. Efficiency is always going to be the smaller number divided by the bigger number. And that will guarantee, oh, and then times 100%. And Natasha, that'll guarantee that you're still in our universe. The reason I say that is sometimes in the grammar of the sentence, the word out will appear in front of what's coming in. Or the word in will appear in front of what's coming out. I'll give you a basic. When you plug something into an outlet, the power coming in is coming from an outlet. So I get confused. You know what? I always just know can't be more than 100% efficient. You ask me to figure out how efficient something is, the smaller numbers going on top. Bigger numbers going to the bottom. A typical household light bulb transforms energy at about 60 watts, 60 joules per second. Most of that energy, however, goes into heat. About 57 watts of power go into heat. About 3 watts of power go into light. So an incandescent bulb is only about 5% efficient in terms of turning energy into light. Kettle might transform electrical energy into heat at a rate of 1500 watts. In fact, most power devices, you can find the power printed on the device for most appliances. Somewhere. Usually on the back or on the bottom. Let's do another question. A mass is being lifted. You know what? Mentally, I would underline the word lifted. And probably constant speed might be important. I don't know. It takes the motor 4 seconds to lift the mass to a height of 12.5 meters. 12.5 meters, about 4 stories, a little less than 4 stories. Okay. Natasha, what does A want me to find? Work. Work equals force times distance. Oh, Natasha, we're lifting. When we're lifting, which force are we doing work against? So I'll even put a little subscripted G right there. Oh, in fact, isn't this this is the one that became MGH, right? Okay. Natasha, what's the mass? Did they give it to me? How big? Yep. 255. G, 9.8, not negative because we're in scalar. What's the height? Good. How many joules of work is this motor doing? That? I'll write down the whole thing and I'll probably round off. So 31237.5. I'll call it 31,000 joules of work approximately, but there's my full answer. Now, Natasha, we can do that amount of work quickly or slowly. If we spread it out over a long time, not as much power required, not as big a motor required. If we let the motor just, oh, if you want it to go really, really fast, need a bigger motor, more powerful motor. Is that all right? Taylor, what's B want me to find? Power is work over time. I just found the work in part A. Did they tell me the time in the question? Oh, okay, it's going to be straight plug and chug. So it's going to be 31237.5. What was the time, Taylor? 4 seconds. Okay. Divide by 4. You get 7,800. I'll call it 7,810. I'll write down the whole thing. 7809.37. 7809.375. 7,800 watts of power. Cool. Luke, what's C want me to find? So efficiency is going to be power out divided by power in. It's going to be the smaller number divided by the bigger number. How much power are we getting out? Power is measured in watt. Okay. How much power are we putting in? Can you read part C to me? 12 kilowatts. I got to change that to watts. 12 kilowatts is how many watts? Nope. It's 12,000. Don't overcomplicate, right? Kilo is 1,000, so 12,000. Pause. Luke, just in case, what's bigger, 12,000 or 7,800? That's going on the bottom. Even if you weren't quite sure. But I think this one's a little more obvious. This is what I'm getting out, but the motor is sucking in that much power. Okay, so it's going to be 7809.375 divided by 12,000. That'll give me a decimal, and then if I multiply that by 100, that'll give me a percentage. And I get 65.1% efficient. That alone suggests to me that this motor is not a gas-powered internal combustion engine motor. It's probably an electric motor. Because gas motors are terribly inefficient. They're usually in the 20s or 30s. Any of you or your folks drive a hybrid? Okay. So again, it's not that radical. You know what? Why not power it with electricity, because you lose far less energy to heat, and then you do need to occasionally recharge it from a generator, but even turning that energy to electricity and driving your car with electricity is more efficient than just turning that energy straight into driving your car. There's other tricks too, like regenerative braking and things, but yeah. Oh, there. Cross out that one, go to example 8. I don't know if you've ever ridden like an exercise bike or done a stair climber or an elliptical or something where they had a digital display that was telling you how many calories you burned. They all have that nowadays. Some of them have a little thing you clip on your finger. It tracks your pulse and all. They're terribly inaccurate. They're terribly inaccurate. But for what it's worth, here's the physics of how they calculate that. Okay? Stair climber on a gym. A 58-kilogram person lifts their center of mass up 18 centimeters with each step. If they take 500 steps in 10 minutes and their muscles are 20% efficient, then, Patrick, can you read A to me, please?
The rate at which the person does work.
Read that out loud again.
The rate at which the person does work.
Everybody stay on this page. Do you know what the rate at which work being done is another word for?
Power.
It's asking me to find power. Okay. Power is work over time. Psst, psst, psst. What will I replace work with?
MGA.
Yep. Over time. What's the mass of this person?
58.
So first thing I would say, by the way, if you're using a training device and it doesn't let you enter the mass, the numbers you're getting back are garbage, because clearly mass is important. 58. G. Now, the height, we're going to have to be clever. How high is one stair in meters, please? 0.018? Just 0.18. Okay, cross out the 18 and make it 0.18 meters. So one stair is 0.18 meters. But how many stairs is this person climbing? The total height is 0.18 times 500. Even though I'm staying in one place, that's what I'm doing against gravity. Divided by time.
10 minutes.
I don't do physics with minutes. Let's all cross out the 10 minutes. How many seconds?
600.
Oh, did you do it in your head? Really? 60 times 10? You use it. Oh, man. heard a phone there, didn't I? Thought I did. Thomas is looking nervous.
What do you mean?
Your watch turned off?
I think it died on me.
Okay. How many watts of power is this person generating? $85.3? Is that right? Before we move on, power is measured in watt? Okay. Before we move on, what if they did it faster? What if instead of 10 minutes, they did it in 8 minutes? More power, same amount of work, more fatigue. What if they did it over 20 minutes? Same amount of work, less power. And that's why the rate at which you exercise changes how many calories are burned or how effective it is for you. It's not just what you do, it's how fast you do it. Can you mute your watch? Because it made a little noise.
Sure.
Or put it in your pocket? Kieran, what's B want me to find? It wants me to find how much power this person put in to get that power out. We're going to use efficiency, which is power out divided by power in. Where is that power in, Kieran? On the top or on the bottom? Ugh. Oh, wait. I think we can times it to the top there, yes? And at the same time, we can divide that there. And this is one of the benefits of exercise, is when you're exercising, it's not just how much work you did in the exercise. Your body actually burned more energy than that. I think we're going to get, Kieran, correct me if I'm wrong, the power in, the rate at which the food energy is used up, is the power out divided by the efficiency. It's going to be 85.26 divided by, what's the efficiency, Kieran? I can't do physics, I can't do math with a percentage. What am I going to put down on the bottom as a number? 0.2. $426.3. That would be the accurate number, but again, an exercise machine has no way of knowing how efficient your body is. So they're taking averages and best guesses and things if they display values. Certainly if they don't ask for your mass, the machine is giving you garbage. And even if they do ask for your mass, they're making a best guess. 426 watts. What's your homework? I'll show you the ones that I assigned my last class. We'll skip some. So you can cross out in the first, there's 2 sections to the homework. For the power section, you can cross out number 3 and number 5. And then for the mixed section, you can cross out number 5, the Gardner question. Sadly, that's it. You need to practice this. But you got 20 minutes or so, 15 minutes to work on either this or your momentum stuff.